Hi everyone, my name is Edwin Rivera and I'm with ALS Environmental. Welcome to our first webinar on siloxanes presented by ALS at our Simi Valley, California laboratory. A few housekeeping items before we get started. This is a webinar series. This is part 1 of 3. The next 2 webinars will be on May 21st and May 28th, so within the next 2 weeks. Each webinar is going to be approximately 20 minutes. This webinar will be recorded, so you'll have access to it on our archive website at alsglobal.com. Participation. It's important for you guys to please participate. There'll be a question section at the end of the presentation, and you'll be able to use the GoToWebinars system to input and ask some questions. And at this time, I'd like to introduce Samantha Henningsen, who is a chemical engineer and a project manager at our Simi Valley facility. Sam has a tremendous amount of experience with air projects, including siloxanes. So Sam, I'll turn it over to you.
Thanks, Edwin. Hi, my name is Sam Henningsen, and as Edwin said, I am a project manager for the ALS Environmental Air Quality Lab. And this is the first installment of the siloxanes webinar series, which will be on what siloxanes are and where they come from. So let's get started. Just as a basic overview of what I'm going to talk about today, I'm going to give you a little intro into the Simi Valley Air Quality Laboratory, where we are, what we do, and then we're going to jump right into siloxanes. I'm going to tell you what they are, speaking as far as chemistry. I'm going to tell you the damage they cause to your equipment. We're going to talk about where they actually come from, as well as how volatile they are. And then at the end, I'm going to leave some space for a basic summary and then hopefully answer any questions that you might have. So, as far as ALS Simi Valley is concerned, we are a 20,000 square foot facility located in Simi Valley, California. Some of you might know us formally as Columbia Analytical Services. We were purchased by ALS in 2011, and we specialize, this particular location specializes in air analyses. We do anything from remediation work to fence line monitoring. We work on vapor intrusion is a huge portion of the work that we do. We do things like passive sampling and indoor air sampling. And we also have a huge market and a huge client base of landfill gas patrons. And when I say landfill gas, I'm talking anywhere from landfills themselves to wastewater treatment plants, digester gas. So all of that is kind of encompassed in what we term as landfill gas patrons. As far as our areas of expertise are concerned, we do everything from permitting and compliance work. That can be things like 40 CFR testing, Tier 2 compliance testing. We do energy content. That could be things like BTU testing or methane content. Methane can also fall under our gas composition analyses. That will be things like fixed gases, so things like oxygen, nitrogen, methane, carbon dioxide, as well as things like VOCs and hydrocarbons. And we can do things like odor and nuisance testing. Now, odor and nuisance testing is kind of a niche market that we have. We've developed a series of analyses that are sensitive enough to meet compounds down at their odor threshold limits. And so while most typical regulatory analyses focus on human health standards, these methods are aimed to go lower than human health standards and get down to that nuisance level where you might have communities complaining of odor issues. And that might be things like sulfur, amines, volatile fatty acids, as well as certain VOCs. The laboratory is DoD certified and NELAB certified, so we're a large commercial laboratory with many different certifications. And as far as the siloxanes methodology is concerned, we brought our siloxane method online in 2011. It's an in-house method we developed ourselves, and we developed it really to meet a client need for landfill gas patrons. As far as the siloxane method is concerned that we have here in the laboratory, I'm going to go into more detail in the third webinar, which will go over everything having to do with our tube method. So I hope you stay tuned in 2 weeks to hear that webinar. So let's jump right into it. Siloxanes, what are they? Well, it's under the family of volatile organic compounds. The term siloxane is actually derived from the words silicon, oxygen, and alkane. So it's kind of a cheeky combination of the 3 words. the siloxanes are labeled according to the number of silicon-oxygen bonds, and as far as siloxanes are concerned, they fall under two categories. You have your cyclical siloxanes, which some of you might know as the siloxanes starting with D, D3, D4, D5, and you can also see a picture of one of the cyclical siloxanes on the left-hand side. And we also have branched chain siloxanes. Those will be your L-containing compounds, or you might know them as MM or MDM. And you can see the branched chain on the left-hand side of that. There are also silanes and silanols. I'm not going to go into too much detail, but there are a number of silicon-containing compounds that you might find in your landfill gas. And so that just kind of summarizes siloxanes as far as the chemistry is concerned. Now, while siloxanes are not necessarily hazardous to your health, they do open themselves up for oxidation. And oxidation most commonly occurs in the form of combustion. So when your silicon atoms are and your siloxane atoms are in the presence of oxygen and heat, they will turn into silicon dioxide, otherwise known as silicon dioxide and water. Your siloxanes, i.e. the higher the D or L number, so L2 and L3 means that they have 2 and 3 silicon atoms respectively, and D4 or potential for silica formation you have. So as you can see, there's 3 silicon atoms in the siloxane compound at the bottom. That's D3, for those of you wondering. And on the right side, you see that there are 3 silica molecules being created. So just keep that in mind for the rest of the presentation. Of the siloxanes, why do you need to worry about them? If they're not hazardous to human health and they're only potentially combustible, what do you need to worry about as far as the siloxane compounds are concerned? And it really stems down to combustion and post-combustion stages of your landfill gas process. Landfill gas typically has ppm levels of the siloxanes, and these siloxanes, which convert into silica using the chemical formula we talked about, or equipment, and potentially cause damage. Commonly affected equipment can range anything from cylinder heads, pistons, turbine blades, heat exchanger surfaces, as well as boilers, and it can cause anything from wear or imbalance. It can cause fouling. It can cause engine power reduction. I was listening to anecdotal information that says that the power reduction might be as much as 10 to 20% on some of your, your combustion engines. It'll cause frequent motor oil changes, as much as twice the prescribed typical amounts, potential engine breakdown, and increased operating costs due to reduced efficiency. So there's a number of problems these siloxanes can cause, and there are a number of different visual symptoms that you can see to show whether or not you need some sort of treatment system, some pre-treatment system. The next couple slides are just going to show some visual markers of siloxane damage, and this first slide has got some combustion engines, and as you can see, the cylinder heads are coated in silica or sand. I mean, that's really what it looks like. It's powdery. It looks like thin grained sand, and so it'll coat anything that it can get a hold of. Again, it's just completely coated with sand. I hear that I have a bit of a technical difficulty, so I'm going to back up to the turbine and microturbine slide, just as a visual indicator of potential siloxane damage. I'm not sure if maybe there was some kind of connection and damage from the silica. And here is the damage on the boilers. Okay. So now that we know their chemistry and we know the damage that they cause, where do they actually come from in the landfill? Well, they can come from household products. Siloxanes are used in cosmetics to soften, smooth, and moisten. They make hair products dry more quickly. Deodorant creams slide on more easily. They're used in moisturizers, facial treatments, as well as many medical implants. And they're also used in water-repelling windshield coatings. So everything that you see here uses a siloxane as a primary ingredient. And this slide was really just put up to show that many items that we purchase, that we use on our body every single day, will contain siloxanes. They're used in plastics and adhesives. Siloxanes are popular additives to plastic products since they provide numerous desirable qualities such as things like flexibility, abrasion resistance, as well as heat resistance. They're used in most commercial plastics as well as things like sealants and lubricants. And my personal favorite is siloxanes are used in synthetic food products. One of the papers I was reading said that siloxanes helped America lose weight. Siloxanes are even used by the food industry as an oil substitute to create low-calorie alternative food products such as potato chips, salad dressings, as well as mayonnaise. And in some fast food applications, a siloxane-based polymer is even used as an anti-foaming agent in some of their commercially fried foods. So they come from all over the place. Now, how do these siloxanes volatilize? How does your ranch dressing that you either consume and ends up in a wastewater treatment facility, or that you throw away the bottle and it ends up in the landfill, how do those siloxanes volatilize and end up in your landfill gas? Well, siloxanes have an average boiling point ranging from about 100 degrees C to 250 degrees C. Now, as a basic parallel, water has an approximate boiling point of 100 degrees C. So that gives you kind of a reference point to start off with. That the most volatile compound is about as volatile as water. And water is liquid at room temperature and ambient pressure, as are most of these siloxane compounds. So how do these compounds turn from the liquid phase into the vapor phase? Well, the quick explanation is it happens through evaporation. In the same way that you see a puddle of water evaporate over time with no added heat or pressure to it, the same way siloxanes will eventually evaporate and volatilize. And the rate of evaporation is dictated by the Clausius-Clapeyron equation. Now, I'm not going to go too much into the calculus of the situation, but the formula was put here just to show that at experimentally derived pressures and temperatures, you can graph a phase diagram, which you can see on the right-hand side, which shows at any given temperature and pressure what phase any given compound might be in. Now, as you can see here in the liquid phase in the middle, this is where the siloxanes typically live at ambient temperature and pressure. So you have only two options for vaporizing your siloxane. You can either raise the temperature or you can lower the pressure. Now, under typical landfill gas applications, you'll actually create a negative pressure differential from your gas extraction system. Blowers are used, it pulls air, creates a vacuum, and lowers the pressure. So that's the simplest way that people end up volatilizing their siloxanes. But another way, and probably a simpler way, is actually just with the general lifespan of your ranch dressing bottle. It goes under tons of waste with time and seasonal and temporal changes, which eventually raise the temperature and assist in speeding up evaporation. Now, you might have any sort of combination of the two to assist in the volatilization of your siloxane compounds, but this was just really said in order to show that there is not always a sense of homogeneity when you are talking about siloxanes and landfill gas. Many clients will complain that their siloxane results differ based off of months or parameters of their gas extraction system or season, and so you're always going to want to keep these items in mind when you do decide to analyze for siloxanes, and then try to create, I guess, a worst case scenario so that you know your maximum siloxane content. So just as a basic summary of what I went over today, I gave you a little overview of the Simi Valley Lab, and then we dove right into siloxanes. We talked about what they are, what they cause, where they come from, and how they vaporize so easily. And from there, I'm going to jump in and give you a little overview of webinar number 2, which is siloxane regulation and analysis, a comparison of current methods to analyze for siloxanes, as well as comparative studies between variously available methods. So if you tune in next week on Wednesday, May 21st at the same time, 10 a.m. Pacific Standard Time, I'm going to give this webinar on current siloxane methods available. I'm going to go into some regulatory oversight, reasons why the methodologies might differ, as well as go into some case studies between variously available methods, which also include the tube method that this particular Simi Valley lab location offers. So thanks for tuning in to the webinar, and from here I'll take any questions that you guys might have.
Sam, great job. That was really, really beneficial information, I think, at least to get us started. And I know that as we move through these webinars, they're going to get more in depth and more in detail. So I think this is a great start. We do have a couple questions. The first question I see is, what are the most common siloxanes found in landfill gas, biogas?
Well, that is a very good question, and it definitely varies from different operations. Now, normally wastewater treatment plants, trimethylsilanol will actually be the most common siloxane constituent, and that's actually siloxane alcohol that I didn't even necessarily go into today. But for typical landfill gas operations, D4 and D5 are usually the most common siloxanes that you'll see in landfill gas. We'll go into more detail in the next few webinars, but you know, that is a common question that people do end up asking. It always depends on, you know, the life of the lifespan of the landfill, how old the landfill itself is at the time, as well as, you know, what kind of materials you're accepting at the landfill. So in the case where commercial plastics are not accepted at wastewater treatment plants, that's why D4 and D5 are not necessarily constituents of concern in those applications.
Yeah, I know we're coming up on the 20 minutes that we allotted for today, but I do have another question here, and maybe we'll do a couple more. You say that siloxanes are present in many healthcare products. Are they listed on the labels? If so, are they called siloxanes, or is there an industrial masking word that is used?
Again, another very good question. Now, many labels will include something, you know, an ingredient that includes the term siloxane, but siloxane is just a very generic term. I mean, for instance, these compounds that I'm talking about, D3, that we saw the chemical formula for, is actually hexamethyl cyclotrisiloxane. So these compounds all have very long names, and they all sound, I mean, kind of convoluted, but they will all contain something with a silicone, you know, some kind of verbiage that includes silicone, siloxane, and I don't think they're always listed, but I'm probably not the right person to ask about those things.
Okay, next question. Have you ever heard of siloxane damage of equipment for environmental remediation systems, for example, SV blowers? Are siloxanes present in the environment or mainly concentrated in landfills?
That's another very good question. No, I haven't particularly heard of siloxane damage in SVE systems, but I don't doubt that it's out there. I mean, we see siloxanes in laboratory air every single day. It's you know, you're probably breathing siloxane-containing compounds in at this very moment. Now, the reason why it's most applicable to landfill gas operations is because it's overly concentrated, you know, in the parts per million levels. And so you're not going to see those kind of levels in ambient air or even in soil gas applications, while we do definitely have other patrons from other, you know, other industries who do siloxane testing. Most of it has to do with industries, you know, car industries, large production facilities, not necessarily vapor intrusion applications.
Ask some questions on the system. We appreciate that, and we'll definitely get you some answers. It just won't be right this second. And so this will be the last question, and then we'll get started next week at the same time. So how do siloxanes reach a gaseous phase in a landfill if the landfill gas is created at around 91 degrees F, much less than 100 degrees C?
Evaporation. I mean, that's kind of what the last slide was utilized for is, excuse me, I'm going to try and go back here. It's dictated by evaporation. While we're not boiling the siloxanes up to their boiling point and vaporizing them, many times people are using gas extraction systems which cause a negative pressure differential. Think about your vacuum cleaner. It's sucking air, well, it's actually pulling air out of the phase, out of the dead space, and it's therefore creating a more volatile atmosphere. So it's evaporation that's causing these compounds to volatilize rather than actually boiling them.
So I was told that we should probably try to answer all these questions, and you're right. If people have to leave, then that's fine. But we'll try to go through as many of the questions as we can here in the next couple minutes. So what effects does dehydrating landfill gas have on siloxanes?
Well, most siloxanes are actually hydrophobic, so it doesn't usually have an effect. The only compounds that it does have an effect on are trimethylsilanol and D3. So for some reason, D3 is soluble in water, and trimethylsilanol, which is an alcohol, almost all alcohols are soluble in water, so that will have an effect, but it does not necessarily have much of an effect on any of the other constituents, D4 and D5 in particular.
Why don't the siloxanes return to a solid if the landfill gas is only 60 degrees F when it reaches the power plant?
Well, that's a good question. Well, I mean, siloxanes are not solid at room temperature. They're liquid, and that's a good question. I'm not sure why they do. I think most of the time it's because the gas is being flared, and so most people don't want to waste the energy in cooling the gas down if they're just going to flare it off again. But I can definitely look into that and get back to you with more information on that.
Why are siloxanes used in beauty products, and what is their purpose? Sure.
Okay, so as far as beauty products are concerned, it's really just for producing a smooth effect. You know, as far as beauty products are concerned, they're used to soften, smooth, and moisten. They're used in hair products to dry quickly. They're just used to create overall a smoothing effect, and so that's really why they're so popular in the cosmetics industry.
Do you see a difference in sampling quality when using Suma canisters versus adsorbent sample tubes?
That is a very good question, and I will have to defer the answer to that to next week's webinar, where we're going to go into the different sample collection methods that are out there, as well as a case study between some. As far as just a sneak peek, though, we did investigate using a Suma canister when we were developing our method, and we found that the sorbent tube actually was more useful for our applications for many reasons, not only for the quality of data that was produced, but also for the kind of sampling that our clients utilize as far as ease, as far as size, as far as shipping weight, as far as hold time, as well as the potential of non-hazardous samples being shipped per DOT regulations. But again, we'll go into more detail about that next week.
Okay, so we'll leave you with that cliffhanger, and we'll look forward to seeing everybody next week. And if you have any questions, feel free to contact us. You can contact. And thank you again for your time, and look forward to visiting with you next week.
Thanks, guys. Talk to you next week.